Hi. Every new project starts with an idea. And from this idea, you build a concept and you make some sketch about it and modify the sketch, improve it. And when you're relatively happy, you start to make a scale drawing of the project so you can be sure that every part fits all together and it fits where it belongs. From there, if the project is not too big or not too expensive, you make a prototype so you can show it to salespeople and see if the commercialization is feasible and if you can have the budget for it. If the project is bigger, more expensive, you have to get a fund for it. If you're inside a corporation, you need to get budget for the development. If you want to make a startup, you need to find outside money from subsidies or from investor. There, a lot of people gonna ask to an artist to make a drawing or simulation of what the project would like and how it should work in the head of the artist. So we have a representation that might be very convicting, but not necessarily represent what's going to happen with the project. And this is a bit embarrassing because now when we present a new concept to an investor or for subsidy people, they are very, very careful because so many times they see nice drawing that at the end produce absolutely nothing as it's supposed to do. Since many years now, we have a new engineering process that called simulation, numerical simulation. This is more and more used by engineers because we have now a very powerful computer, very affordable. So we can make a lot of calculation. This needs a lot of calculation and come to a point that you have some information that are very precise. Computer simulation is an engineering process that you can split in 5 big steps. First, you have to make the numerical drawing of your prototype, which everybody knew today as an AutoCAD design. And the second element, the second part, you have to split this design in a large quantity of very small part that's going to interface all together, that's going to work all together, that's going to simulate what's really going to happen with the project you have developed, however it's physical, electric, or fluid dynamics. Third step is to define exactly what's the environment, which project it is. It's air, helium, aluminum, plastic, and what's move, what's turn, what's fixed, what temperature it is. When everything is very clearly set, the computer can make the calculation. And the last step, you have to extract from the data, the base you produce, you have to extract the information that is useful for your process. A good way to understand how computer simulation works is to understand the meshing, how it's working. That's a good principle, so let's see a few images of it. So, as you see, a meshing is the computerization of a lot of small cells that work all together to give a figure, to make a numerical representation of the object of the prototype you want to analyze. So this matrix is set with dots that give the position of all the cells and the interaction in between cells, and the interface with each cell is done by one face. Every face of one cell faces only one face of another cell, and the temperature, the pressure, the momentum, everything passes through this face to make the equilibrium. In our concept of vertical axis wind turbine, we use a 2D simulation, which is give us the exact information we need, and the simulation we does use 35,000 cells to make a good evaluation of the project, and the computer need to make a 6-second real-time simulation of the turbine. The computer have to make about 100 times the calculation on every cells to make on every component of the cells to make sure that everything balanced. So it's quite a heavy process. When you have the machine and you have set all the parameters that you need for the simulation, the calculation is done. You have a database that includes a lot of information. You have to extract this information, and you can take it. You can analyze information one by one, or sometimes by a set of few ones, to visualize what's happening exactly on your project. So let's see some image. So you see many images of what happened around a pail of a turbine, pressure, speed, and turbulence, and those images need to be seen at every step. That the turbine, all the pail make permanent rotation, and every step is different. So you have to understand at every step what's good, what's give torque, and what's give drag, what stop the turbine. So at the most important position, where you got the most torque, you can make analysis of where you have a lot of pressure. If this pressure help you to give torque or stop, the pressure that sometimes give you more torque. In this case, this is the depression that gives the torques, and the pressure stop it a bit. And you see it everywhere, and from there you see, okay, this maybe I can change this, and it's going to be better. Maybe I change that, and it's going to be better. And there's a lot of change that you can do. You make a new drawing, you make a new simulation, and the computer going to give you the torque, the final torque of each item. So you're going to be able to see if you really improve your pail. This simulation, in addition, going to give you the force on a pail. So you're going to be able to determine if the pail is strength enough, is strong enough to resist to all the force that's going to be applied on it. And you can determine on the overall turbine what's going to be the pressure, what's going to be the force of the wind, and it gives you very important information on the structure of the wind turbine. If you want to build a project that's going to last for 50 or 100 years, you need those information. Let's note finally that the pail you saw in the presentation was a NACA pail, a NACA standard pail number 63415 that is very often mentioned on research for vertical axis wind turbine. On our simulation, this pail never gave more than 35% efficiency in front of wind. The pail and the turbine we have developed, because the turbine is a set of pail, produce between 50 and 53% of efficiency for many wind speed, starting from 6 to 16 meters per second. So from what we have, we can guarantee that our wind turbine is going to have an overall average efficiency of at least 40%, most probably a little more, and with some speed, it most probably peak nearby 50%. So thank you for your attention.